Hi, this is the second of 3 COMSOL videos that I'm preparing for the Medical Diagnostics Bioengineering 167 class. So in this video, we're going to use COMSOL to simulate a very simple microfluidic device that has convection and diffusion occurring in it. This won't be our biosensor. This is just going to be a little microfluidic demo device, but it will get us acquainted with what it takes to combine both the laminar flow and the transport of dilute species modules within COMSOL. And then in the third of these videos, we'll combine all that together and apply it to our biosensor. So, but first, we're going to connect to the VPN as usual. There we go. And I'm going to launch COMSOL. Okay, here we go. All right, so we'll start with the model wizard as usual, and so we're going to be doing the usual 2D simulation. And now in the last video, we used just transport of dilute species. In this video, we're going to add 2 physics modules. First, the laminar flow one, which will solve our fluid flow problems for us. And then second, we'll add transport of dilute species. In this example, we'll use that and the ability to visualize the concentration of solute C. We'll use that just as a way to follow fluid along inside of our device and visualize how things mix and behave on the microscale in our device. Okay, so I'll click on to study. Now in this case we can use a stationary study because unlike last time where we had only diffusion operating and we had to choose a time-dependent study, in this case we could choose either one, but for simplicity I'm going to choose a stationary study, so we're going to see the behavior of this microfluidic device at a steady state, at a constant behavior. Okay, so here's our default view here. And so I can see first the length unit that I'm going to change to something a little more appropriate, like millimeters for a microfluidic device. And then I'm going to zoom out a bit so I can see a few millimeters worth of space here. And I'm going to start to draw my device. So what we're going to create here as a demonstration device is a classic cross or T-channel, and I'm going to make it out of 3 rectangles. Here's the first one. That'll be the long channel, and then I'm going to add in 2 additional rectangles, one here and one here. That will be my my side channels. I might even lengthen this one here a little bit. Okay, very good. So that's the device, and I'll zoom to extend so we can see the whole thing. What we're going to create here, we'll have 3 inlets, one here, and one there, and one outlet there. And the interesting things happen here in the middle where we can see what this shape and this section of channels does to fluid flow here in the very middle. Okay, the next stop is to assign a material to everything. So I will add a material from the library, and I'll select liquids and gases, liquids, and water, and I'll select add to component, and in a moment the whole channel network here should turn blue, indicating that water has been assigned to all those domains. There it goes, and I can see domains 1, 2, and 3 over there listed, so that's correct. Okay, close that, and so now we're back to this overview here. The next step is to look at the laminar flow module and see what the defaults are. Under fluid properties, everything is being defined, like density and viscosity are being defined from the material, water, as it should be. The initial values of everything is to not have an initial velocity inside of here. We're going to use inlets and outlets to create the flow inside of this that we want, so that's correct. And the initial boundary conditions are walls for everything all the way around, which makes sense. So, so that's good. And then we can glance under transport of dilute species as well. We see the initial transport properties. Again, no convection field to start, but I'm going to highlight something very important here, and I am going to change this at this early stage. The velocity field must not be 0. It must be instead using the velocity field SPF that we calculated up here in our laminar flow module. So this is a very important correction, or not a correction, but a little change I have to make to the COMSOL's defaults to make sure that the transport of dilute species module is using the velocity field that we computed up here in the laminar flow module and not the default, which is a constant 0. So there, I've done that. Now the 2 modules are linked together. The boundary conditions under transport of dilute species default to no flux, which makes sense. The solutes neither going in nor out of the system by default, and the initial values of the concentration throughout this are 0. In our previous simulation, we specified a concentration here because that was a way to basically tell the model that would tell COMSOL that we have preloaded a particular concentration into this. We're not going to do that. In this case, the solute is going to come in from from one of our inlets over here, what COMSOL calls an inflow. But we'll get to that in a minute. But for now, there's nothing stopping me from building the mesh. Looks good, and I can actually perform my study here just to confirm that everything is working at this early stage. So we'll let that run for a moment. And we get a number of plots out over here. These are going to be very boring plots because we are not doing anything very interesting, but I still like to simulate at this early stage to confirm that everything is working as expected. For the velocity plot, we see 0 meters per second of magnitude of velocity vector throughout the entire device, which is correct. We're not intentionally flowing anything yet. There's no pressure drop across the device, and the concentration of our solute throughout the device is also 0. So far so good. Okay, so let's start back up here at laminar flow, and we're going to add some inlets. So I'm going to select an inlet. The selector toggle here is active, which means I can select the domains that I want to be inlets. I'm going to choose that one, and that one. And then under the velocity here, I'll specify a normal inflow velocity of, say, 1 millimeter per second, a reasonable flow rate for a little microfluidic device of this size. And then under laminar flow again, I'll right-click and select outlet. And I will, in a minute, select the outlet boundary, and then that defaults to saying no pressure at that boundary, which is sort of akin to saying atmospheric pressure, an open exit to the atmosphere there. So that's all good. At this point, I could simulate it again and confirm that the fluid flow is working as I expected. So I'll right-click on Study 1 again and simulate it, and there we go. Looking at the velocity plot, we see what we were more or less expecting. Regions of low flow here in the inlets, but then when all three of those flows combine into the main horizontal channel, we see a higher flow there in the middle, and we see the parabolic distribution of flow rates, ranging from dark red here in the middle of the channel where the flow is the highest, all the way to blue and low flow at the very edges of the channel walls. So all that makes sense. I see a little granularity here in the middle of the channel. That reflects the coarseness of the mesh in this region here. So I guess if I'm being a little gutsy, I could try to increase the density of the mesh just a bit and see if that reduces that granularity any. I'll run my study again. Of course, if I go with too fine a mesh, I may be making the simulation take too long. Yeah, I think that helped a little bit. So anyway, that's good enough. Under pressure, I can see in a moment here a series of lines of equal pressure showing a pressure drop along the channel, which makes sense. And under concentration, there's still nothing there because we haven't intentionally introduced a solute into this system yet. Okay, so let's do that next. Under transport of dilute species, I will right-click and select an inflow. Inflow is COMSOL's term for a boundary that will be providing solute at a specified concentration, and I'm going to select this middle inlet here, and then I will specify here 1 mole per cubic meter concentration. That's 1 millimolar, I believe, a reasonable concentration of our solute to be adding into our system. And then for conservation of mass, I also have to have a place for that to go, and so I'm going to add an outflow at the channel exit there. Okay, very good. I think that's enough to be able to simulate this again. So I will run compute, and it should update our solution. Very good. There's the velocity picture again, which hasn't changed any, but if I look at concentration, now I see a very different story going on here, and this is exactly the phenomena that I wanted to highlight to you here. Interestingly, the concentrations up here and down here aren't what I expected, and I realize why that's the case. In hindsight, I only added one inflow, which set the flow in at this interface here to be 1 mole per cubic meter. I didn't intentionally set the concentrations at either of those or those, and so this little red and blue pattern here is because COMSOL is assuming that by diffusion, the red stuff would enter into this at a certain concentration, and the blue stuff would enter into that. That's not the behavior that I intended to show you. I intended to add a second inflow that is assigned to these other two inlets. So let's do that now, and then the results will make a little more sense. So this inflow will be assigned to these two inlets. It will have a concentration that I won't change here of 0 moles per cubic meter. So that's what I forgot last time. So what you see here are two inflows, one inflow of 1 mole per cubic meter concentration at the middle, and then a second inflow of 0 moles per cubic meter concentration of our solute, meaning no solute at all in those, or just water at those two inflows. Okay, Let's run the simulation again, and this should make a little bit more sense. Okay, there's a velocity view again, and there we go. Now on to concentration. This is what makes sense. I was thrown a little bit because I didn't expect to see red in these sections here, because I was intending to send just water into those, which wouldn't have the red color in it. Okay, so let's take a step and look at what we see here. So here's our red stuff. This is our dye or our solute, whatever, going into this middle channel here. And then it's being pinched, what we call sort of pinched flow, by these two side channels here that don't have the red contents to them. But you can see what effect that has to this. This flow of fluid here gets pinched and narrowed down. It accelerates. We know that from the velocity view here. It accelerates and it grows thinner and then turns into this long, thin streamline, and it mixes, it dilutes a bit in the flow. You see what was red goes to these oranges and yellows, and eventually the cyan color. But what we see is we don't see full mixing, at least by the end of this little channel that we are simulating here. And indeed, that's as we expect in these microfluidic devices. In this device, we have, haven't calculated it here, but probably a very low Reynolds number that lends itself to laminar flow and very slow mixing times. We see viscous dominated behaviors inside of this device. So what we've made here is not a terribly good mixer. And so a fun challenge is to try to design a different channel geometry, a different sets of inlets and outlets that might make for a better mixer. But in this case, what we can say is that the fluid that was in this has been lined up here in the middle of the channel and accelerated and is now heading down in this direction. Now, a structure like this is encountered in lots of different diagnostic instruments. For example, in a flow cytometer, this might be the sample of cells or whatnot that you're trying to analyze. And then by flowing into a flow focusing structure like this, the population of cells gets spread out to the point that we have perhaps a single line of single cells going down this section here, where they then interact with the laser beam and emit fluorescent light or whatever it is that you're trying to measure in the flow cytometer. So this is a not uncommon structure, not just in microfluidics, but also in other diagnostic bioinstruments. Okay, so we've accomplished what I wanted to show you in this video. In the third and final video, we'll combine everything you've seen up to this point and apply it to our model biosensor. Okay, that's all for now.